Okay, welcome back to our lecture on computer programming for engineering applications. So previously, we explored the concept of string in C programming, and remember that strings are essentially sequences of characters, and when it comes to handling input and output operations with string in C, we rely on two fundamental functions, which are puts and gets. As function serve as our tool for managing input and output operation with a string. And we also need to include the string.h header file that will grant us access to a variety of built-in functions tailored specifically for string manipulation. And among these functions are some key functions, which are the string compare, which compares to strings and returns a value indicating their relationship. And we also have string concatenate that concatenates two strings, and also we have the string length that calculates the length of a string, and we have also a string copy which copies one string to another. And this function will help us to perform a range of string operations efficiently within our C programs. So in this last video, we're going to talk about structures, unions, and enumerations in C programming language. So by the end of our session, you'll be able to write a programs that leverage compound data structures like structs and unions. And these structures are vital for organizing and managing complex data in C programs. And you'll also be able to distinguish between a struct and a union in terms of their memory allocation. And the last one is you will be able to use enumerated data types in your programs. And these enumerated data types will provide you a convenient way to define a set of name constants that will make your code more readable and maintainable. So now let's discuss the concept of structure variables in C programming. So structures are different from arrays in several ways. So firstly, the properties of a structure diverge from those of an array. So while arrays are comprised of elements of the same type, structures allow for members of different types within a single entity. And secondly, each member of structure possesses a distinct name. And this is different with arrays where elements are accessed based on their position. While in structures, we select a specific member by specifying its name rather than its position within the structure. And also worth noting that in some programming languages, structures are referred to as records, and their members are known as fields. And this naming convention may vary across different programming paradigms. However, the underlying principles will remain the same. And now let's explore how to declare structure variables in C programming. So structures serve as a practical solution for organizing a group of related data items into a cohesive unit. So imagine we have a scenario where we need to store information about parts in a warehouse. And we can create a structure to encapsulate this data. Here in the slide, we have an example how we can declare two structure variables to represent part in our warehouse. So in this declaration in our slide, we define a structure containing three members: the number, name, and on hand, and each member represents a specific attribute of a part. Number is an integer representing the part number, and name is an array of characters allowing us to store the name of the part. And on hand is an integer indicating the quantity of the part available in the warehouse. And by declaring structure variable part 1 and part 2 of the structure type, we create instances that can hold data for two different parts in our warehouse. And this approach will help us to organize and manage related data efficiently, making our code more structured and easier to understand. And now let's see the memory organization of structured variables in C. So when we declare a structure, its members are stored in memory sequentially. Now let's consider an example using structure variable part 1, which represents a part in our warehouse. So we'll make some assumption to illustrate how part 1 is laid out in memory. So first we assume that part 1 is located at memory address 2000, and integers typically occupy 4 bytes of memory. And next we have a constant name length defined with a value of 25, and there are no gaps or padding between the members of the structure. And given these assumptions, let's visualize how part 1 is structured in the memory. Here we can see on the right side of the slide, at the memory address 2000, the number member occupies the first 4 bytes, and next the name member is stored, and since the name is an array of characters with a length of name length plus 1, it occupies a contiguous block of memory starting from the address 2004 and continuing for 26 bytes. And finally, the on-hand member follows, occupying the next 4 bytes, and the sequential arrangement ensures efficient memory utilization and allows us to easily access each member of the structure. So here's the simplified representation of our structure that we've discussed before. So the member of each values, which are the number, name, and on-hand, will go in these boxes later. Now let's discuss an important concept related to declaring structure in C, which is the scope. So when we declare a structure, we're essentially defining a new scope within our program. And this means that any names declared within the structure, such as the member variables, will not conflict with name used elsewhere in the program. So in simpler terms, you can think of a structure as a container that encapsulates its own set of variables, separate from the rest of the program. As isolation ensures that the name used within the structure are unique within that scope and will not cause conflicts with name used elsewhere. So in C terminology, each structure has its own separate namespace for its members, and this means that even if you use the same variable names in different structures or in other parts of your program, they are considered distinct in one class with each other. Now let's explore how we can declare multiple structure variables within the same program in C. So for instance, in our program we can have declarations for 2 different structures, the one representing parts in our warehouse and another representing employees in a company. And here in the slide we can see the example of how these declarations might look. So in the code that we have here in the slide, we have to separate structures defined. The first structure, part, consists of members representing part number, part name, and quantity on hand. And we declare 2 variables of the structure type, which is the part 1 and part 2. And similarly, the second structure, which is the employee, contains numbers for employee name, employee number, and gender. And again, we declare 2 variables of the structure type, which is the employee 1 and employee 2. And each structure has its own set of members, and we can declare multiple variables of each structure type within the same program. And now let's discuss initializing structure variables in C. So just like other variables, we can initialize structure variables during declaration, providing an initial values for their members. Here in the slide we have a example that where we declare two structure variables part 1 and part 2 representing parts in a warehouse, and we initialize them with specific values. So here each structure variable is followed by an initializer enclosed in curly braces, and within the braces we provide values for each member of the structure separated by commas. So for part 1, the values 5 to 8, disk drive, and 10 are assigned to its number, name, and on-hand members respectively. And on part 2 is initialized with values 914, printer cable, and 5 for its members. And after this initialization, the part 1 will contain the values we specified, and also will happen to the part 2 of our program. And now let's discuss how to initialize structure variables in C. So this process is quite similar to those when we're trying to initialize an array. So in C, expressions used in a structure initializer must typically be a constant. However, it's important to note that this restriction was relaxed in the C99 standard, allowing for more flexibility. And when we are initializing a structure variable, we can provide fewer members in the initializer than there are members in the structure itself. And in such cases, any leftover member in the structure will be automatically assigned a default initial value of 0. So for instance, let's say we have a structure representing a point in a 3D space with member for x, y, and z coordinates. So if we initialize a variable of this structure type with only two values, such as 10 and 20 for the x and y coordinates, and the z coordinate will be defaulted to 0. And this behavior ensures that all members of the structure are initialized, even if not explicitly specified by us when we're trying to initialize it. And here we're going to discuss about a feature introduced in C99 standard called designated initializers, which can be used with structures to provide more clarity and flexibility when we're initializing our structure. So here we have an example in our slide here, the orange code. So with a designated initializer, we can label each value with the name of the member it initialized, like the brown code that we have in the slide here. So in this initialization, each value is preceded by a period and the name of the corresponding structure member it initialized. For example, dot number equal to 528 initializes the member with the value 528, and the dot name equal to disk drive initializes the name member with the string disk drive, and so on. And the combination of the period and the member name is called a designator. And designated initializers provide a clear and explicit way to initialize structure members, especially when we're dealing with structures that have many members or when the order of the members is not intuitive. And one significant advantage of designated initializers is that they enhance the readability and the ease of checking for correctness. And by explicitly labeling each value with the name of the corresponding structure member, designated initializer make it clear which value is assigned to which member. And this clarity can greatly reduce the likelihood of errors and makes the code more understandable, especially when we are dealing with structures that have many members. And the another advantage is the flexibility they provide in the order of initialization values. So unlike traditional initializers where values must be placed in the same order as the member listed in the structure, designated initializers allows values to be assigned to members in any order. This means that the programmer doesn't need to remember the exact order in which the members were originally declared, making the initialization process more intuitive and error-resistant. And furthermore, the use of designated initializers allows for greater flexibility in modifying the structure in the future. And since the order of the members can be changed without affecting designated initializers, and structural changes can be made more easily without requiring corresponding changes to initialization code. As flexibility promotes code maintainability and reduces the risk of errors when modifying our structure. So in a designated initializer, not all values need to be preceded by a designator. And this means that some values can be provided without explicitly specifying the number they initialize. So instead, the compiler assumes that these values correspond to members in the order they appear in the structure definition. So for example, we have initialization example here in the slide. So in this initializer, the value disk drive is not preceded by a designator. However, the compiler understands that it initializes the member that follows number in the structure. So in this case, disk drive initializes the name member of the structure, which is on the second position. Additionally, any members that the initializers fail to account for will be automatically set to 0, and this ensures that all members of the structure are properly initialized, even if not explicitly specified in the initializer. And if we want to access a member within a structure, we can use the structure variable's name followed by a period and the name of the member we want to access. So for example, let's say we have a structure variable part1 that we've discussed before that represent a part in a warehouse. And to display the values of its members, we will use statements like the one here in the bottom of the slide. So in each printf statement, we specify the format specifier, which is the D for integers and S for strings, to match the data type of the member being displayed. And we use the structure variable name part1 followed by a period to access the specific member, which can be number, name, or on hand, and we pass the member's value as an argument to the printf function. And it's also important to understand that structure members are considered ELF values. It means that they can appear on the left side of an assignment statement or as the operand in an increment or decrement operations. For example, here in the slide, the part1 number equal to 258 and the part1 on hand increment. So in the first code, we assign the value 258 to the number of the part1 structure variable. And statement modifies the part number of part1, allowing us to update its value as needed. And in the second code, we use the increment operator, which double positive sign on the on hand member of part1, and this statement increments the quantity on hand of part1, allowing us to track changes to the quantity in the straightforward manner. And the period that we use to access a structure member is actually a C operator. It is known as the member access or dot operator. This operator takes precedence over nearly all other operators in C. So for instance, we have the following code in the slide. So in this example, we use scanf to read an integer value and store it in the on-hand member of part1 structure variable, and the ampersand operator is used to compute the address of part1.onHand, which is then passed to scanf as the argument for storing the input value. And it's important to note that the dot operator takes precedence over the ampersand operator. And this means that the dot operator or the member access operator is evaluated for the ampersand operator in the expression. As a result, the address of part1.onHand is computed correctly. And it allows scanf to modify the value of onHand within the part1 structure variable. And now let's discuss another fundamental operation on structure in C, which is the assignment. So when we assign one structure variable to another, such as part2 equal to part1, it has the effect of copying the values of each member from part1 to part2. So for example, if part1 has the following values, like part1 that numbers 5 to 8, and part1 that name is disk drive, and part1 that on hand is 10, then after the assignment part2 equal to part1, the part2 will also have these values copied into its corresponding members. So part2 number will be set to 5 to 8, part2 name will be set to disk drive, and part2 on hand will be set to 10. And this assignment statement copies each member of part 1 to the corresponding member of part 2, and it's useful for copying entire structures that allows us to duplicate data and manipulate it independently, and it ensures that both part 1 and part 2 hold the same information. And now in C, arrays cannot be copied using the equal operator directly or the assignment operator directly. However, an array embedded within a structure is copied when the enclosing structure is copied. And its property can be useful in certain situations. So for example, some programmer exploits behavior by creating dummy structures to enclose arrays that will be copied later. And this trick is quite interesting and it's quite useful. And here we have an example here in the slide. In this code, we have two structure variables a1 and a2, and both of them contain an array of integers with 10 elements. And when we use the assignment operator to assign a2 to a1, the entire contents of the array within a2 are copied into the corresponding array within a1. And this kind of operation, this kind of approach is legal because a1 and a2 are structures, and structures can be copied using the equal operator. And this trick can be useful when we're trying to copy arrays by embedding them within this structure, and this provides us a shortcut for implementation of direct array copying in C. So instead of we are looping through the array, we can just copy it directly using the structure. And the assignment operator, which is used for assignment, can only be used with structure of compatible types. And so structures declared at the same time, such as part 1 and part 2, are compatible because they have the same structure definition. And additionally, structures declared using the same structure tag or the same type name are also considered compatible. This means that if two structures share the same structure tag or have been defined with the same type name, they can be used interchangeably with the assignment operator. And it's important to note that other than assignment, C provides no built-in operations on entire structure. So for example, the equal or not equal operators can be used directly within structure to compare their contents. So instead, if you need to compare structures for equality or inequality, you would typically need to compare their individual members one by one. And suppose that a program needs to declare several structure variables with identical members. So in such cases, it's beneficial to have a name that represents a type of structure, not just a particular structure variable. And there are two common ways to name a structure. First one is to declare a structure tag. So a structure tag is a name given to a structure type, and it's declared for the opening curly braces of the structure definition. And the second one is to use the type def to define a type name. And this keyword, the type def, allows us to create an alias for a data type, including structure types. And now let's discuss more about a structure tag in C. So a structure tag is a name used to identify a particular kind of structure. So it serves as a label for the structure type, and it allows us to reference and use it in our program. And to declare a structure tag, we use the struct keyword followed by this desired tag name, and then an opening curly brace followed by the definition of the structure members, and finally a closing curly brace. We can see the example here in the slide. So this example, part is the structure tag, and it represents a type of structure that contains members for a part number, a name, and a quantity on hand. And it's important to note that a semicolon must follow the closing curly brace of the structure definition, and this indicates at the end of the structure declaration. And by declaring a structure tag, we create a reusable type that can be used to declare multiple structure variables throughout our program. And now once we have declared a structure tag, such as the one in our previous slide, we can use it to declare variables of that structure type. And this allows us to create multiple variables that share the same structure definition. So for example, here we have the part structure, and in the example that we have in this slide here, the part 1 and part 2 are variables of type part, and they're capable of storing part numbers, names, and quantities on hand as defined by the structure tag part. And it's important to note that we cannot drop the word struct when declaring variables of structure type. The second example here in the slide is incorrect because part is not a type name, because part is not a type name on its own, and without the word struct it is meaningless in the context of variable declaration. And since structure tags are only recognized when preceded by the word struct, they do not conflict with other name used in our program. And when we are declaring a structure tag, we simultaneously declare structured variables of that type. And this allows us to define a structure and create variables of the structure type in a single statement. So for example, in the code that we have in the slide here, we declare a structure tag named part, and this declaration is immediately followed by the structure definition and the structure variables part 1 and part 2, and these variables are of type part and have the same structure definition as specified by the structure tag. And this combined declaration provides a convenient way to define a new structure type and create variables of that type in a single statement. And it's worth noting that the structure definition is enclosed within the curly braces, is followed by a semicolon. And this will ensure the structure definition is complete before moving on to the declaration of structure variables. And now let's discuss the compatibility of structures declared with the same structure tag in C programming. So all structures declared to have the type struct part are compatible with one another, and this means that if we declare multiple structure variables using the same structure tag, they can be used interchangeably, and assignments between them are valid. So for example, here in the slide, if we perform an assignment between part 1 and part 2, this assignment is legal because both part 1 and part 2 have the same structure type, which is the part, and they share same structure definition and therefore are compatible with each other. And this compatibility allows us to assign the values of one structure variable to another, facilitating the manipulation and management of structured data in our programs. Now, instead of declaring a structure tag and then using it to declare variables, we can use typedef to define a genuine type name for a structure. So for example, here in the slide, the typedef is used to define a new type named part, which represents the structure containing members for a part number, name, and the quantity on hand. And now we can declare variables of type part in the same way as a built-in types. And here the part 1 and part 2 at the bottom of our slides are variables of type part, and they can store the part numbers, names, and quantities on hand just like any other built-in types in C. And when we're using typedef to define a structure, this allows us to create a more concise and readable code, and it eliminates the need for explicit structure tags, making the code cleaner and more intuitive. And typedef enables us to create reusable type names, enhancing code clarity and promoting consistency in our program. And now let's discuss how structures can be used as an argument and return values in C functions. So functions in C can accept structures as arguments and return structures as values, providing a convenient way to work with structured data within a function. And here we have a function in slide. So in this function, the print part, the parameter p is of type struct part, and which means it accepts a structure of type part as an argument. And within the function body, we can access the members of the structure p using the dot operator or the member access operator and print their values accordingly. We can see how we can call this function at the bottom of our slide here. And this slide demonstrates how structures can be seamlessly integrated into function arguments, allowing us to pass complex data structures to functions for processing. And now let's begin by examining a function that returns a structure. So here in the slide we have this function here. So in this function build part, it takes 3 arguments, which is an integer number, a string name, and an integer on hand. And then it creates a structure p of type struct part and assigns value to its members, which are number, name, and on hand, and returns the structure. And in the code at the bottom of our slide, we can call this function like this and assign its return value to a structure variable. And this approach illustrates how structures can be conveniently returned from functions and allows us to encapsulate complex data structures and manipulate them effectively within our programs. And now in this function, the f function, we have a new structure part 2 that's declared and initialized with the structure part 1 from the argument of the f function. And this kind of initialization allows us to create a copy of the structure part 1 within the function scope, and we can then perform further operations on part 2 as needed. And it's important to note that the structure being initialized, which is the part 2 in this case, must have automatic storage duration. This means that the structure variable is created and destroyed within the function scope. So in chapter 9 before, we have introduced a feature of C99 known as compound literals. Now let's explore how compound literals allows us to create structures on the fly without the need to first store them in a variable. A compound literal is a convenient way to create a structure directly within an expression. And this kind of approach will provide us with more flexibility in passing structure as parameters, or when we are trying to return them from functions, or when we're trying to assign them to variables. So now let's see how a compound literal can be used to create a structure that will be passed to a function. Now we have the example here. in the first code in our slide. So in this example, the struct part that's enclosed by the parentheses with 528 disk drive and 10 enclosed in curly braces is a compound literal representing a structure of type struct part, and the values 528 disk drive and 10 are provided as the initial values for the structure members, and this compound literal is then passed directly to the print part function as an argument. And next, let's see how a compound literal can be assigned to a variable. Here in the bottom of our slide, the compound literal struct part 528 disk drive 10 is assigned to the variable part 1, and is effectively initializing it with the specified values. And this approach provides us with a concise and efficient way to create and initialize structures in C. And they can be particularly useful in scenarios where temporary structures are needed, or when we are initializing structures directly within function calls or assignments. And also, compound literal can be used with designators, and it could handle partial initialization. So here in the slide we have the following example. Here the code that printed in orange. So in this example, the compound literal, which is the struct part, the onHand10.name disk drive.number 528, initializes a structure of type struct part, and designators are used to specify the values for specific members of the structure, providing clarity and flexibility in initialization. And it's important to note that a compound literal may fail to provide full initialization for all members of the structure, and in such cases any uninitialized members default to 0, and this behavior ensures that the structure is properly initialized even if some members are not explicitly provided in the compound literal. So now in C, the versatility of structures and arrays allows us to combine them without any restrictions. So this means that the arrays can contain structures as their elements, and structures can also contain arrays and even other structures as their members. So next we're going to talk about nested structure. So nesting one structure inside another is a common practice and very useful. So this approach will allow us to organize and represent complex data in a hierarchical manner. Now here we have the example of a person name structure, and we have 3 members for the structure: the first name, the middle initial name, and last name, and each member stores a specific part of a person's name. The first member is an array of characters representing the person first name, and the middle initial member stores the middle initial of the person, and the last member is an array of characters representing the person's last name. And now, based on our previous person name structure, here in this slide we can use the person name as a part of a larger structure. So here, let's say we want to create a structure called student, which represents information about a student, including their name, student ID, age, and sex. And we can use the person name structure as part of the student structure. So in this student structure, the name member is of type struct person name, which means It contains all the members defined in the person name structure, and additionally we have members for ID, age, and sex to store information specific to the student. And to access the members of the person name structure within the student structure, we use the dot operator twice. So for example, to assign a first name to student 1, we will write the code in the bottom of our slide here is a string copy student1 dot name dot first and fret. And here is student1 name first refers to the first member of the name structure within the student1. And by nesting structures in this approach, we can create more organized and comprehensive data structures that will accurately represent real-world entities, such as students with their personal information. Now, utilizing nested structures over several advantages, especially when dealing with complex data entities like names. And now, let's discuss how nested structures streamline data handling. So consider the person name structure we discussed earlier, which encapsulates a person's first name, middle initial, and last name. And now imagine we have a structure called student, which we have in our previous slide before, where student information. And now in C, arrays and structure often work hand in hand, like I've said before. So one common use case is an array of structures where each element of the array is a structure. And this combination is particularly useful and can be likened similar to a simple database. So for instance, consider an array named inventory where each element represents information about a specific part. We can define the array like the one we have in the slide here. And here we've created an array named inventory, capable of storing information about 100 parts. And each element of the array is a structure of type part, which includes members such as number, name, and on hand. And this setup mirrors a simple database where each row corresponds to a part and each column contains attributes of that part. And in our case, each element of the array represents a part, and the members of the structure hold details like part number, name, and quantity on hand. So when we're accessing elements within these arrays, this will involve a combination of subscripting and a member selection. So to access a specific part within the array inventory, we use subscripting. We can see the example here, first code of our slide. And here inventory at index I refers to the element of the array at the position of I. And once we have accessed a specific part, modifying or accessing its member requires a member access operator. So for instance, to modify the number or member of a part within the array, we can use the inventory at index I dot number equal to 883. And in this line, the inventory will select the part at the position I from the array, and that number accesses the member of that part, allowing us to assign it a new value. And similarly, to access and modify individual characters within the name member of a part, we use subscripting followed by member selection here. So in the bottom of our slide here, the inventory at index I selects the part at the position I, and .name accesses the name member of that part, and the index 0 selects the first character within the name array. So initializing an array of structures follow a similar pattern to initializing a multi-dimensional arrays. So each structure within the array is initialized individually, and the array initializer encapsulates all the structure initializer. And one of the reasons for initializing an array of structure is this is particularly useful when the data it contains remain constant throughout the program's execution. And now let's consider the scenario where we need to store country codes for international telephone calls. And in this case, the array elements will consist of structures, with each structure storing the name of a country along with its corresponding code. Here in the bottom of our slide, we define a structure named dialing code to represent each country code pair. And here, country is a pointer to a string representing the name of the country, and a code is an integer storing the corresponding dialing code. Now here in this example, country codes is an array of structures, with each structure representing a country along with its corresponding dialing code, and the const or the constant keyword indicates that the array is read-only and its element cannot be modified. And each element of the array consists of a structure value where the country name is paired with its respective dialing code, and the inner braces around each structure value are optional but can enhance code readability. So in C99 there's a more flexible way when we're trying to initialize an array of structures by using designated initializer. So designated initializers allows us to specify which members of structure are being initialized within an array initializer. So let's consider an example where we initialize an array of structures called inventory. So each element of this array represents a part with information such as the part number, quantity on hand, and the name. So here in the slide we have the example of the code. You can see that each initializer is preceded by the index of the array element it initializes within the square brackets, followed by the member designator. And designator initializer offer a more concise and precise way to initialize array elements, especially when only a few members needs initialization or when the order of initialization differs from the order of member declaration. Now let's discuss unions. So in C we have another composite data type called a union. So like a structure, a union consists of one or more members, each of which can be of a different type. However, there's a significant difference in how memory is allocated for unions compared to structure. So when you declare a union, the compiler allocates memory space only for the largest member within that union. This means that all members of the union share the same memory location, but only the memory space required by the largest member is allocated. And what's interesting is that because the members of a union share the same memory space, modifying one member can affect the values of other members. And this is because all members overlay each other within the allocated memory space. So assigning a new value to one member can potentially change the values of other members as well. This memory saving feature makes unions particularly useful in situations where you need to represent different types of data in a space-efficient manner, or when you need to access multiple types of data using the same memory allocation. And here we have an example. So we declare a union named U, and inside this union we have two members, I, which is an integer, and D, which is a double. Now let's compare this to a structure declaration that we have here in the bottom of the slide. We have a structure named S with the same members I and D. And at first glance, the declaration of a union may seem similar to that of a structure. However, there's a fundamental difference between them. So, like I've discussed before, unlike structures where memory is allocated for each member individually, unions allocate memory only for the largest member. And this means that the unions share the same memory space for all their members. So, based on our previous examples, the structure S and the union U. So while they both contain members I and D, their memory allocation differs significantly. So for a structure S, each member is allocated its own space in memory. This means that I and D have distinct memory address, and as a result, any changes made to one member will not affect the other. But on the other hand, in the union U, all members share the same memory address. This means that I and D occupy the same memory space, and consequently, modifying one member will overwrite the memory contents affecting all other members. And this distinction in memory allocation is crucial to understand when working with unions. And like structures, we access union members using the dot operator. So for instance, if we have a union U, we can assign values to its members I and D, like the one here that we have in the slides. However, there's a crucial difference with unions. So changing the value of one member affects all other members because they share the same memory space. So for example, if we store a value in u.d, any previous value in u.i will be overwritten and lost. Similarly, modifying u.i will corrupt u.d because they both occupy the same memory location. And this behavior underscores the importance of careful handling when working with unions. So unions share many characteristics with structures. We can declare union text and types in much the same way as we do with structure. And furthermore, unions can be manipulated in similar way to structures. We can copy unions using the assignment operator, pass them as arguments to functions, and even have function return unions. So despite their differences in memory allocation, unions and structures share common ground in terms of how we declare, use, and manipulate them in our programs. And unlike structures, where we can initialize individual members, unions have a limitation. So only the first member of a union can be given a initial value. So for example, for a union we have here in the slide. So to initialize the I member of this union to 0, we can use the syntax here with u equal to curly braces 0. So however, it's essential to note that the expression inside the braces must be a constant, and this is a requirement in C, although the rules slightly differ in C99. And in a union, designated initializers allows us to specify which member of the union should be initialized. And this means that we can explicitly choose which member to assign a value to. We can see the example here in our slide. And it's important to note that only one member can be initialized at a time, but it doesn't necessarily have to be the first one. And one significant application of unions is in space saving or memory saving. So since unions only allocate memory for the largest member, they can be more memory efficient when compared to structures, especially when dealing with varying data types. And another common application is in building mixed data structures. So union allows us to combine different types of data within a single structure, like a struct, for example, and providing flexibility in representing complex data. And additionally, unions are useful for viewing storage in different ways. So like we've discussed before, unions can serve as a valuable tool for optimizing memory usage, especially when we're dealing with structures. Now let's consider a scenario where we're designing a structure to store information about items sold through a gift catalog. And each item has common attributes like a stock number and a price, but they also have specific attributes depending on their type. So for instance, books have additional attributes such as title, author, and number of pages, and mugs might have a design attribute, while shirts could have attributes like available colors and sizes. Now instead of allocating memory for each possible attribute for every item, we can use unions within the structure. And this way, memory is only allocated for the largest member of the function, resulting in space savings. So this is our initial approach on designing a structure to represent items that sold through a gift catalog. So we start with a structured name catalog item, and the structure aims to encompass various types of items, including books, mugs, and shirts, and to accommodate the diverse attributes of these items, our structure includes several fields which are stock number to uniquely identify each item, and a price to indicate the cost, and then the item type to denote the type of item, and we have the title, author, and pages for books, and then design for mugs, and colors and sizes for shirts. And while this approach seems comprehensive, it has drawbacks. So each instance of catalog item reserves memory for all its fields, and regardless of the item type, as a result, memory may be wasted for attributes that aren't applicable to certain items. So currently our structure includes fields such as item type, colors, and sizes to accommodate various types of items in the catalog. However, this approach leads to inefficiencies as it reserves space for attributes that may not be relevant to all items. So for instance, the item type field can take on values like book, mug, or shirt, indicating the type of item. Meanwhile, the colors and sizes store encoded combination for respective attributes. However, it's evident that not all items in the catalog require the same set of attributes. So for example, books don't have color or size variation like mugs or shirts do. And to address this issue, we can introduce a union within the catalog item structure. And this union allows us to define different types of items with varying attributes while efficiently utilizing the memory. And here we have the revised catalog item structure that now incorporates a union. So this approach, this version, allows us to accommodate various types of catalog items while minimizing memory overhead. And within the structure, each item is characterized by its unique set of attributes. For instance, a book is described by its title, author, and number of pages. And on the other hand, a mug is defined solely by its design, while a shirt encompasses design, colors, and sizes. And by utilizing a union, we ensure that only the relevant attributes for each item are stored in our memory. And this will reduce the overall space required by the structure. So if C is a catalog item structure that pertains to a book, so to print the book's title, we will typically access it through the nested union that we can see here in our slide. So this approach, while functional, can be deemed cumbersome. So accessing a union nested within a structure requires explicit specification of the union's member corresponding to the item type. And while nested unions offer space efficiency, they may introduce complexity in code, readability, and maintenance, especially when dealing with multiple item types within the same structure. So conventionally, it's cautioned against storing a value into one member of a union and subsequently accessing the data through a different member. However, there exists a scenario where this practice can be deemed acceptable. So consider a scenario where two or more members of the union are structures, and the structures commence with one or more matching members. So in such cases, if one of the structures is currently deemed valid, then the corresponding matching members in the other structures will also be considered valid. As phenomena underscore the interconnectedness and synchronization between union members, allowing for a degree of flexibility in data access and manipulation within the catalog item structure. So within the catalog item structure, a union is used and it will store three distinct structure as its members. And among these structures, both the mock and shirt begin with an identical member, which is design. And now, suppose a value is assigned to one of the design members within the union. We can see the example here in the first code in our slide. So following this assignment, the design member in the other structure assumes definition and inherits the same value. And consequently, accessing the design member within the shared structure yields the identical value. So this gives us example about the synchronized behavior between the members of the union, where changes made to one member seamlessly reflect across other members that share common attributes. So unions serve as a versatile tool for constructing data structures that combines data of diverse types seamlessly. Now suppose there's an array that requires elements comprising both integer and floating point values. And to do this, we define a union type with a distinct varieties of data for storage within the array. And this union type named number that encompass two members, that is I for integers and D for doubles. And these union types gives us the groundwork for accommodating an array that will accommodate a blend of integer and double data. And by leveraging unions, we can custom our data structures to adapt on accommodating a various type of data types. So utilizing unions facilitates us to construct data structures that capable of storing a different types of data. And to give example, we can see here an array that's designed to store a combination of integer and floating point values that we have seen in our previous slide. So here we have the number array, which comprise of elements of type number, and this number type is a union that we've defined before in our previous slides that can encapsulate either an integer or a double value. And given that a number union can store either an integer or double value, we can exploit this flexibility to introduce a combination of integer and floating point data within our number array. So for instance, in the bottom of our slides here, we assign an integer value of 5 to the first element of our number array, and second element receive a double value of 8.395. So in a union, discerning which member was most recently modified and holds our data presents a challenge. And to illustrate, let's suppose we have the task of crafting a function tasked with showcasing the value that's stored within a number union. So we can see this function in our next slide. So in this code, we encounter a function named printNumber designed to print the value stored within a number union. However, the absence of indicator within the union poses a challenge. So here the function lacks the ability to ascertain whether the number unions holds an integer or a floating point number, and consequently attempting to print its value becomes an uncertain effort. And to fix this ambiguity, we can use something called as tag field within the number union. And this field serves as a marker indicating the type of data stored within the union at any given time. So like I've said before, we can use the tag field to keep track of our latest data that stored in the union. And this additional feature within a union acts as a marker that provide a clarity regarding the content of the union. So for instance, consider the item type member within the catalog item structure that we have previously. So this member serves precisely as a tag field that fulfill the role of indicating the type of data that currently held within the union. And by embedding the union within a structure containing a tag field, we can have a structured approach to manage the information within the union. And incorporating a tag field into a union can greatly enhance its usability and clarity. And here we have an example showcasing the integration of tag field within a structure that houses a union. Now consider the number type, which is defined as a structure encompassing an embedded union, and within the structure we introduce a tag field named kind. And this tag field serves as a marker indicating the type of data that currently stored within the function. And to facilitate clear identification, we assign numeric values to represent the different kind of data. For instance, integer kind is designated as 0 while double kind is designated as 1. So in the structure, the kind member assumes the role of the tag field, with its value indicating whether the union currently holds an integer or a double. And each time we assign a value to a member of the union, we simultaneously update the tag field to indicate which member was modified. And let's consider an example where we assign a value to the integer member I of the union. And in this scenario, we ensure that the tag field, which is the kind, is updated accordingly to reflect that an integer value is now stored within the union. And here n represents a variable of type number, and which comprises the union u along with the tag field kind. And by updating the tag field whenever we modify a member of the union, we maintain clarity regarding the type of data stored within the union at any given time. And when the number stored in a number variable is retrieved, this kind field will tell us which member of the union was the last to be assigned a value. And here we have a function that takes advantage of this capability. So within this function print number, we utilize the kind field to determine the type of value stored within the union u of the number variable n. So if kind indicates that the most recent value assigned was an integer, the function prints the integer value stored in n.u.i. And conversely, if kind indicates a double, the function prints the double value stored in n.u.d. And by leveraging this tag field kind, this function adapts its behavior based on the type of data stored within the number variable, ensuring accurate and appropriate output regardless of the data type stored within the union. So in programming, there are instances where we require variables to hold values from a small predefined set of options. And consider a scenario where we need to represent the suit of a playing card So in such cases, it's impractical to use regular variables with arbitrary values. Instead, we can employ enumerations to define a distinct set of meaningful values. And enumerations, often abbreviated as enums, allows us to declare a custom data type consisting of a finite list of named constants. For instance, to represent the suits of playing cards, we can define an enumeration called suit with the following members: clubs, diamonds, hearts, and spades. And here each member of the enumeration represents one of the four possible suits in a deck of cards. And enumerations provide a structured and intuitive way to define variables that have a limited number of meaningful values. So, a pseudo variable can be declared as an integer with a set of codes that represent the possible values of the variable. So here in the example in our slide, we have integer s, which will store a suit, and s is equal to 2, which represents heart. However, there are significant drawbacks to this approach. So first, using numeric codes like 2 to represent hearts can be cryptic and it lacks clarity. And without additional context, it's not immediately obvious that each numeric value represents. And the second one is that there is no inherent constraint on the possible values of the variable. And we cannot tell from the declaration that the variable should only have 4 possible values, corresponding to the 4 suits of a deck of cards. So here we have another approach where we use macros to define a suit type, and for every macro's name we have an integer value that corresponds to each type of card. And at the bottom of our slide here we have an updated version from our previous example. So the problem with the example in our previous slide, we discussed using macros. So while this approach works, it has its own drawbacks. So one of the issues that the same one with first example, which is lack of clarity regarding the relationship between each macros. So when someone reads the program, they may not immediately recognize that clubs, diamonds, hearts, and spades all belong to the same type. And another challenge arises when dealing with a large number of possible values. So defining separate macros for each values became cumbersome and error-prone. And furthermore, macros like clubs and hearts are removed by the preprocessor, making them unavailable during debugging. And this can hinder the troubleshooting process and make it harder to understand the code. So C provides a special kind of type to handle such cases that we've discussed before more efficiently. And this special type is called enumeration. So an enumeration type, often referred to as an enum, is designed specifically for variables with a small predefined number of possible values. So with enumerations, programmers list out all the possible values that a variable of that type can hold. And for each value in an enumeration, we assign a unique name known as enumeration constant, and this constant serves as a symbolic representation of the possible values, which make the code more readable and easier to understand compared to our two examples before. And although enumerations is different with structures and unions, they share a similar declaration syntax in C. So to define an enumeration, we use the enum keyword followed by a list of possible values and close in braces. And each value is assigned a unique name known as enumeration constant. Here we can see the example in our slide here. And it's essential to note that the names of enumeration constants must be distinct from other identifiers declared in the same scope. to avoid any conflicts. And enumeration constants, although resembling constants created with the defined directive, it also have a distinct characteristic. So when an enumeration is declared inside a function, its constants are scoped within that function and are not visible outside of it. And this encapsulation ensures that the enumeration constants do not interfere with other parts of the program. So unlike constants created with define, which are processed by the preprocessor and substituted with their values throughout the code, enumeration constants retain their symbolic names and treated as distinct entities by the compiler. So similar to structures and unions, enumerations in C can be named using two methods. First is by declaring a tag or by employing typedef to establish a genuine type name. So enumeration tags follow a structure and union-like syntax. Here we can see the example in our slide here. First code, so suit is the enumeration tag, and the constants clubs, diamonds, hearts, and spades represent the possible values of the enumeration. And to declare variables of this enumeration type, you'll use the enum keyword followed by the tag, like the one we have in the bottom of our slide. And by doing so, S1 and S2 are declared as variables capable of storing one of the enumerated values, which are the clubs, diamonds, hearts, or spades. And another approach to naming enumeration is by utilizing typedef to establish a type name. So here, first code in our slide, we have an example here. So in this example, suit is defined as a type name for the enumeration containing the values of clubs, diamonds, hearts, and spades. And with this definition, S1 and S2 are now variable of type suit. And using typedef in this manner is particularly useful in C89 for creating Boolean types. So here, bool becomes a type name representing the enumeration with values false and true. So in C, enumerations are essentially integers under the hood. So by default, the compilers assign a consecutive integer starting from 0 until the last constants in an enumeration. So for instance, in the suit enumerations that we have before, the clubs is assigned the integer value 0, the diamonds is 1, hearts is 2, and spades is 3. As integer assignments facilitate efficient representation of enumeration constants in memory and enable easy comparison and manipulation. So in C, you have the flexibility in assigning specific integer values to enumeration constants. So for instance, we can see here in the slide, you can explicitly assign different integer values to each enumeration constant. So here clubs is assigned the integer value 1, diamonds is 2, heart is 3, and spade is 4. And additionally, you can assign arbitrary integer values to enumeration constants without any particular order. So in this example, research is 20, and production is 10, and sales is 25. And it's legal for multiple enumeration constants to have the same value if necessary. So in C, when you don't specify a value for an enumeration constant, it automatically gets assigned a value that is 1 greater than the value of the previous constant. So here we can see in this example here black is implicitly assigned value 0 because it is the first enumeration constant, and light gray or LT gray is explicitly assigned 7, and dark gray or DK gray automatically gets assigned 8, which is 1 greater than the light gray, and white is explicitly assigned 15. And in C, enumeration values can seamlessly coexist with ordinary integers. So here in the slide we can see some code. So the variable s of the type enum that we have here behaves like any other integer variable. So we assign it the value 0, which corresponds to clubs, incrementing s by 1, which will make it into diamonds, and then we perform arithmetic operation using s, such as adding 2 to it and then storing the result in I. So essentially, clubs, diamond, hearts, and spades serve as a symbolic names for the integers 0, 1, 2, and 3. So in C, while it's useful to interchange between enumeration values and integer, there's a problem. So using an integer as enumeration value can be risky. So consider this scenario where suppose we inadvertently assign the number 4 to a variable s meant to represent a card suit. However, 4 doesn't align with any suit in our enumeration. And this assignment can lead to unintended consequences or errors in our program. Therefore, it's essential to be cautious when handling enumeration values and ensure that we use them appropriately to prevent such issues. So enumerations are particularly useful for tracking which member of a union which was most recently assigned a value. So consider the number structure that we have here in our slide. So instead of representing the kind member with an integer, we can define it as an enumeration. So by using an enumeration for the kind member, we provide clarity and improve readability in our code. And now when accessing or manipulating data within the union, we can rely on the enumeration to ascertain the type of the data that we stored. So incorporating enumeration as a tag fields in a structures over several advantages over using macros or plain integers. So with the new structure, the usage remains consistent with the previous implementation. However, we eliminate the need for integer kind and double kind macros, simplifying our code base. And moreover, by utilizing enumeration, we explicitly convey that the kind member can only take on two distinct values, which is the integer kind and double kind. Its clarity enhances code comprehension and reduces the potential for errors. And here we have the inventory.c program that will demonstrate the practical application of nested arrays and structures. As program is designed to manage a warehouse inventory system, specifically tracking various parts stored within. And at its core, the program utilizes an array of structures to store information about each part. And the contents of each structure are the part number, which stores a unique identifier for each part, and the name that holds the descriptive name or label of the part, and then the quantity, which denotes the quantity of the respective part available in the inventory. And there are several operations that's supported by the program. First one is adding a new part. So users can input a new part number along with its corresponding name and initial quantity on hand. And this functionality facilitates the integration of new parts into the database. And second one is printing part informations. And by providing a specific part number, the users can retrieve essential details such as the part name and its current quantity on hand. And the third one is changing quantity. So users have the capability to modify the quantity on hand for a particular part by specifying its part number. And we also can print the database information. So program allows for the generation of comprehensive tables displaying all information stored within the database. And the loss function is to terminating the program. So upon completion of desired operations, users can terminate program execution. And the codes I for insert, S for search, U for update, and P for print, and Q for quit will be used to represent the operation that I mentioned before in the previous slide. And here in this slide we can see an example of a session with the program. Here also shows a session with the program showing another functionality of the program, which is the insert and the update. And here we can see the session when the user want to print the overall information from the database. So the program will store all the information about each part in a structure, and the structures will be stored in an array named inventory. And we also have a variable named num_parts that will keep track of the number of parts that currently stored in the array. And here's the outline of our program main loop. So the program will prompt the user to enter operation code, and it will read the code, and it will read the appropriate operations from the code using switch case functionality, and it will go back again into the first line in the for loop. And the program will also define separate functions that will perform the insert, the search, update, and print operations. And since the functions will all need to access the inventory and num_parts, these variables will be external. And the program is going to be split into 3 files, which is the inventory.c, which is the main program, and then we have the readline.h, and then we have the readline.c that contains the definition of readline. And for information, readline.h is a header file that will store the prototype for the readline.c. And now let's see the code for our inventory.c program. So first, here we have the include for start library, the start input output, and then we also include the readline function that we have in another source code. And we also define the name length is 25, and then the maximum number of parts, which is 100. And here we declare a part structure which contains the number, the name, and the quantity on hand for each part. And here we also have the number of parts that currently stored, and we also have prototype for each of our operational function. And here is the main function of our code. So here we define a code variable, and here we have an infinite for loop, and the program will prompt the user to enter the operation code, and using the switch case statement, it will decide which operation that it will do. And here in the bottom part of our code, we have our function, the find part, that looks up a part number in the inventory array, and we have the insert function to insert a new part here, and we also have search function that prompts the user to enter a part number, and it will looks up the part in the database. And this function connected with our find part function before. And we also have update to update the quantity of our part, and we also have print that will print a table for all of our parts in the database. And now let's see the read line here. This is the header file that stores the prototype for our readline function, and this is the source code for our readline function. So this will skip the white space for our input. Now let's see this program when we run it. So let's try to insert. Okay, now let's try to print our database. Here you can see that the input is reflected in the output for the print operational function. And now let's quit this program. So when we define a structure, we have two options for naming it. We can either declare a structure tag or we use typedef, and the choice between these two options depend on the specific requirements of our programs. However, it's important to note that declaring a structure tag becomes mandatory in certain situations, such as when the structure is intended to be used in a linked list. And linked lists, which covered in chapter 17, which we're not going to cover in this course, are a fundamental data structures in computer science, and they consist of a sequence of elements, each containing a reference to the next element in the sequence. So when we pass a structure to a function or return a structure from a function, a copy of all members in the structure is made, and this copying process incurs some overhead, especially for large structures. And to minimize this overhead and improve efficiency, it's often advisable to pass a pointer to a structure or return a pointer to a structure instead of passing or returning the structure itself. And by passing a pointer to a structure, we avoid the need to make a copy of the entire structure, as we are only passing the memory address where the structure is stored. And similarly, when a function returns a pointer to a structure, it avoids the overhead of copying the structure's member by simply returning a reference to the structure's memory location. And chapter 17 that we're not covering in this course provide example of function that accept a pointer to a structure as an argument and or return a pointer to a structure. And these examples demonstrate how using pointers can improve program efficiency, especially when dealing with large or complex structures. So there are other reasons to avoid copying structures. So for example, the start input output header defines a type name file, which is typically a structure, and each file structure stores information about the state of an open file and therefore must be unique in a program. And every function in start input output header that opens a file returns a pointer to a file structure. And every function that performs an operation on an open file requires a file pointer as an argument. So compile literal is formed by enclosing a type name within parentheses, followed by a set of values enclosed in braces. So when creating a compile literal that represents a structure, the type name can either be a structure tag preceded by the keyword struct or a typedef name if a typedef has been defined for the structure. Okay, we've come to the end of our lecture today, and so let's wrap it up. So in summary, structs, unions, and enumerations are fundamental concepts in C that allow for organizing and manipulating data in various ways. So struct, short for the structures, are variables that can hold a collection of related data items, and these Data items do not have to be of the same data type. So for example, a struct can store information about a person, including their name, age, and address, all in one variable. And unions are similar to structs in that they can also store a collection of related data items. However, unlike structs, unions allocate memory in a way that only one member of the union can be accessed at a time. And this makes unions useful when you need to conserve memory and only one piece of data needs to be stored at any given moment. And enumerations or enums are used when a variable can only take on a small set of meaningful values. And they provide a way to define name constants within a program, making the code more readable and understandable. So for example, you can use enums to represent the days of the week or the suits in the text of a cards. So in conclusion, structs, union, enumeration are essential tools for organizing and working with data in C programming. And by understanding how to use this concept effectively, you can write more efficient and maintainable code. So I think that's all that I have for this video. I hope you have a great journey learning C and maybe other programming languages in the next semester. And if you need any help, just reach out to me or Pavita, and we'll help you as soon as possible. Thank you and have a great journey.